All right, guys. I really thought my stylus for my computer was at home, and it is not. So we're going to do what we can. I'm going to write with my finger. It's going to be slightly annoying. I might actually just kind of work from my key, and that's okay. We'll be all right. So this is going to be the lessons, or lesson number 2 of quadratics. We're going to kind of split it into 2 portions. So your first page here says properties of quadratic functions. So a quadratic is in the form y equals ax squared plus bx plus c. So where you have x to the power of 2, where a, b, and c are numbers. We looked at yesterday how changing the value of a, b, and c change different properties of the graph. So for example, changing c changes where your y-intercept is. So the graph of a quadratic function is called a parabola. I believe I said that yesterday, so that's just the shape that a graph makes. Every quadratic function will have a vertex, that being the, oh, no. Now will it let me do stuff with my finger? Let's see. So again, the vertex is the highest or lowest point on the curve. Again, it's going to have a highest point if it's opening downwards. So this is the highest point of this graph. That's the vertex. We sometimes will end up calling that the maximum. Sorry, you're not going to be able to read me writing with my pointer finger, but that's the maximum. If we had a parabola that opened this way, your vertex would be the minimum. So just depending on the direction of opening, it will always have a vertex, and we'll either call it a maximum or minimum value, which I see now is that second point. All quadratic functions will have a y-intercept. Not all of them have an x-intercept, and a pretty good example is this one. So it's opening upwards, and the vertex is above the x-axis, so at no point does it cross the x-axis. So this portion, it says list the coordinates of the x-intercepts of each graph on the right. So I know yours is in black and gray and white, but you can kind of see it in colors here. So this red graph, we're going to call graph 1, and then this blue graph we're going to call graph 2. So just looking at the x-intercept, so this first one, point 1 here, is at -5, 0. So again, whenever you write coordinates, you write the x-coordinate first and then the y-coordinate. So it's at -5, 0. Then point 2, it's kind of hard to see which is which, but point 2 is this point here, and it is at 1, 0. And then point 3 is this point right here, and it is at -2, 0. And finally, point 4 on graph 2 there, over on the right, is at 3, 0. And so it's saying what's similar about each of the coordinates. And it should be pretty obvious is the y value, or the y coordinate, is equal to 0. And it says explain if this will always be the case. Yes, it will be the case because the y value of an x-intercept is always 0. Because the x-axis is the line y is equal to 0. So along here, just up on the graph here, it's not very straight, this is the line y equals -6. This is the line y equals -4. This is the line y equals -2. Your x-axis is actually the line y is equal to 0. So, there we go. So it says use the x-intercepts to determine the axis of symmetry for each graph. graph 1 and graph 2 and draw the axis of symmetry on the graphs. So for graph 1, actually, will it let me erase that if I write bigger? No, I didn't. Oh, I need to do this. Yeah, this is next level annoying, but we will get by. So the axis of symmetry, I'm going to just shorthand because the less writing I do, the better. The axis of symmetry will always be halfway between 2 points that have the same y value. So you don't have to draw this out, but if we had a parabola here, your axis, that's really badly drawing parabola, and that's even worse drawn axis of symmetry. But again, it should be where it folds over. So any points that have the same y value will be the same distance from your axis of symmetry. So if those have a y value of 1, they're going to be the same distance. If these have a y value of 2, they're going to be the same distance. So that's what I mean by your axis of symmetry is always halfway between 2 points that have the same y value. So, oh gosh, I don't have a copy of my notes in front of me, so I don't know what the points are. So for graph 1, we have an x-intercept at -5 and an x-intercept at +1. So what we need to do to figure out halfway, so graph 1, is we're going to add those two values together. So -5 plus 1. And we're going to divide that by 2 to get halfway between. For graph 2, we have points of -2, +3. So we go -2 plus 3 divided by 2. So -5 plus 1 is -4 divided by 2 is equal to -2. For graph 2, -2 plus 3 is +1 divided by 2 is equal to +1/2. So the axis of symmetry for graph 1 is the line x equals -2, and the axis of symmetry for graph 2 is the line x equals 0.5 or x equals +1/2. So we could scroll back up, sorry, pause it if I've flipped ahead of you and write that down. I will scroll back up and we can kind of draw it on the graphs that I've made a real mess of by scrawling all over it. So now looking at our axis of symmetry for graph 1 was along the line x equals -2. So this is as good as I can get, but this is the line x equals -2. And for my blue, it was at half, +1/2. So this is the axis of symmetry for graph 2. It's at the line x equals 1/2 or x equals 0.5. Those are our axis of symmetry. And so this definition here is kind of important, that the axis of symmetry will always be halfway between 2 points that have the same y value. I'm just going to quickly, oopsie, peek at my notes, see if I wrote down anything else different. That's looking pretty good. If you're annoyed with my notes, this looks a lot neater in the key that I have, so you might want to snap photos of the key instead of trying to follow along with what I'm writing on my tablet right now. So those were our axis of symmetry. So on to the next one. So we started off the semester by reviewing factoring stuff from 10C, and I said it's important more so in the second unit, being able to factor a trinomial, either by inspection, if your A value is equal to 1, we can use inspection, or if your A value is not equal to 1, so if it's equal to 5, we can use decomposition. You can use decomposition if A is equal to 1. It just kind of like adds on a step, but you can use decomposition all the time. But I just, love my lazy ways, and inspection's a little bit easier, potentially. So we're looking at this one. This is going to be important, our ability to factor trinomials, because we can get some pieces of information from a factored trinomial. So we have a quadratic function here, so it's not equal to a number. We have a quadratic function, so f of x, or if you wanted to just write y instead of f of x, y equals x squared minus 2x minus 3. So if we want to write it as, if we want to factor it, make it into a product of two binomials, this is what we mean by factoring. By inspection, we're looking for two numbers that multiply to be equal to -3 and add to be equal to -2. So multiply to be equal to our C value, add to be equal to our B value. So I know if they multiply to be a negative, one needs to be positive, one needs to be negative, and since they add to a negative number here, I know my bigger one needs to be the negative. So thinking about factors of 3, 1 and 3, that's really the only way you can go with this. So we know it needs to be -3 and +1, because those multiply to be equal to -3 and they add to be equal to -2. So what that tells us is that when we write our binomials, x plus 1, x minus 3. Sorry if that's hard to read. That says x plus 1 and x minus 3. So it says there, we know for all x-intercepts, the y value is equal to 0. So what we're looking for in this case is what makes each of those little factors that we have, so x plus 1 and x minus 3, equal to 0. The only way to get an answer of 0 is if one or both of the factors is equal to 0. Again, because we're multiplying, if this one's equal to 0 and we multiply by anything else, it's still equal to 0. So if one or both of the factors are equal to 0, that would make everything equal to 0. So what we need to analyze is what makes each of those equal to 0. So if we're looking at x plus 1 is equal to 0 and x minus 3 is equal to 0, what value for x, this is what we're doing here, is we're solving each of these simple equations for x to find the x-intercepts. So in order to solve this first one for x, I know I need to subtract 1 from both sides. What I do to one side of the equation, I must do to the other. So x is equal to -1. And then for the second equation, add 3 to both sides. What I do to one side or the other, I must do to the other. So x is equal to 3. So these are the x-intercepts. So our factored, if we can factor, then we can find the x-intercepts from that. Ah! By setting equal to 0. Sorry, I know that's kind of running out of room. So it says once we know the x-intercepts, we can sketch the graph of the function. So we can figure out the y-intercept. We know that from the original equation. Our investigation yesterday told us that when we're in the form y equals ax squared plus dx plus c, our y-intercept comes from this c value. Maximum or minimum, we know the parabola opens up or down from the original equation. So when you have a positive leading coefficient or a positive a value, So if positive A, it opens up. If it's a negative A, it opens down. Sorry, that's impossible to read. If the A value is positive, it opens up. If the A value is negative, it opens down. The x-intercepts we know from factoring up above. And the axis of symmetry, we did this kind of on the front page, that once we have the x-intercepts, we can find the axis of symmetry. And the way that we did that on the front side is going to be halfway between the x-intercepts or any 2 points with the same y value. That says halfway between x-intercepts or any 2 points with the same y value. And from there, I'm saying a lot of and from there, this is going to be a big process, we can use the axis of symmetry to calculate the maximum or minimum value. Our vertex, again, that's either a maximum or a minimum. Uh-oh. Max or minimum is always on the axis of symmetry. So if we, sorry, you might need to write that, so pause it. I'm going to flip back. If we look at this, so these graphs that we had earlier, you can see that for my graph 1, my vertex is right here, and it's right on the axis of symmetry. And for my graph 2, this one has a minimum, but my vertex is on the axis of symmetry. Okay, are we done with this page? I think we're done with this page. So now it says, let's get busy. So what I mean by let's get busy here is what we're going to do is we're going to try to sketch out this graph without using our calculator. So doing the algebraic process behind how we can find out basically everything for this graph just based on this equation. Now, that's not saying you can't lightly scam the system and just put it in your calculator and trace your vertex, trace your x-intercepts, trace your y-axis or your y-intercept. Figure out your axis of symmetry kind of from that. So graphically is always there for you, and please don't feel like you need to hide if you're doing it graphically. Graphically is important, but I promise you that on a test somewhere, I will say sketch a graph of this function algebraically, meaning you're secretly putting it in your calculator and verifying your answers, but we're going to look at the whole algebraic process behind it. So this, if I'm not mistaken, is the same as this. Yes. So we know a couple of things. I'm going to kind of follow this function summary, but I'm going to write a lot over here as well. So know that once you start writing, don't write too huge because it does take up quite a bit of room. So our y-intercept. Also, if you want to just listen and not write it down, I can then flip to my key, which is a million times easier to read, and you can write it down from that. So our y-intercept, we know, is the c value of the function. So our y-intercept is where it crosses the y-axis. So it's going to be at coordinate -3. Again, this is our c value, 0. So if I feel so inclined, boop, boop, I'm going to put a point right here. And I'm probably going to write it on my function summary because I'm doing it all right now. So -3, 0 is our y-intercept. And again, that's because the y-intercept is the c value of the function. So in order to figure out our direction of opening, that's the next part here, is looking at if it opens up or down. Since our a value is greater than 0, it's a positive a value, we know that it's actually going to be opening up, upwards, up, however you want to write it. I'll write that over here just so we're going through all the steps. Since a is greater than 0, opens up. Again, if a was less than 0, so if a was a negative value, it would be opening down. So to figure out x-intercepts, we actually did this process above. So to figure out the x-intercepts, you need to try to factor. So above we had y equals x squared minus 2x minus 3, and we set that equal to 0, because again, your x-intercepts are when y is equal to 0. And then we factored it. So I'm not going to go through the steps again. This is just the question at the top. We factored that trinomial. So it was x minus 3 times x plus 1. And then we figured out the x-intercept by setting each of those individual factors equal to 0. So we said, again, x minus 3 equals 0, and x plus 1 equals 0. And then we said, if we added 3 to both sides of this first equation, x is equal to 3, and x is equal to negative 1. So our x-intercepts are at 3, 0, and negative 1, 0. So 3, uh-oh. I goofed with my, hopefully you're yelling like uncontrollably at me, because this is definitely not a y-intercept. Y-intercept has an x value of 0, a y value of negative 3. At least I drew it right, but I wrote it down wrong. This is why I said maybe use my key when I put it up later. So sorry if you have to erase. Your y-intercept will have an x value of 0. So your x-intercepts, at least I was going right there, are at 3, 0, and negative 1, 0. Oh, can't quite go that far off my page. And so plotting those on my graph as well. 1, 2, 3. Oop. And then negative 1. Oop. So I can see the shape of my graph, right? Like I get a pretty good sketch. But we want kind of all of the things that should be represented properly. So to figure out our axis of symmetry, again, we're going to do halfway between x-intercepts. So what we do is we take the value for those x-intercepts, add them together, and divide it by 2. So 3 plus negative 1 divided by 2. So 3 plus negative 1 is 2. 2 divided by 2 is 1. So the axis of symmetry is the line x is equal to 1. And so usually, if you're drawing that on, you'll just kind of maybe draw it as a dotted line, maybe in a different color, just to not confuse yourself. So that's the line x is equal to 1. That's our axis of symmetry where it should fold over itself. Okay. So then it says maximum or minimum value. So if we know this is opening upwards, we're going to have a minimum value. We're going to have a lowest value. So it has a minimum value. So vertex, in this case a minimum, will be on the axis of symmetry, which is the line x equals 1. So what I can do is I can sub in x equals 1 into the original equation. And so we already know, just up in our little function summary, that the x value for our vertex is going to be 1 because it's on the axis of symmetry. So we're just trying to find the y value if x is equal to 1. So the original equation, oh my gosh, so x squared minus 2x minus 3. Anywhere there's an x, I'm going to put 1 in. 1 squared minus 2 times 1 minus 3. And now we're just solving for the y value that corresponds to an x value of 1. So 1 minus 2 minus 3. So 1 minus 2 is negative 1, minus 3 is negative 4. So y equals negative 4. So 1 and negative 4 is where the vertex is. And that should make sense with what we've drawn so far, right? You wouldn't have the vertex up above like your x-intercept. You wouldn't have a vertex here. That doesn't make sense. You would have a vertex down here. So it's at 1, negative 4. So it's right here. And you can write in all your coordinates as you go. So this is at 3, 0. This is at 1, negative 4, and so on and so forth. I'm not going to do it all. So once we've done all of that, the only thing that we have left is domain and range. So I'm actually going to connect my little happy dots now. Boop. Boop. So that is our very beautiful sketch of the graph. Whoa-wee. So domain and range. So again, your domain is looking at your x values. Your range is looking at your y values. And so our x values, like I said, this is just going to keep going up and apart and up and apart. And I could keep extending the page upwards and it keeps going out, meaning that for every x value, there is going to be a corresponding y value way up the graph. So our domain for this is actually nice and easy. So x is an element of the real number system because there is all possible x values for just a function like this. Our range, however, so our range, we see that if I drew a line across y equals negative 5, it doesn't actually touch our graph anywhere. So our graph has a minimum value. So we actually have restrictions on our range. And what we would say is y needs to be greater than or equal to negative 4 because that's where the vertex is. It's at the point y equals negative 4. So the graph is everywhere above that y equals negative 4. And we would probably still say y is an element of the real number system because it's every y value above that. So those are our domain and range. So maybe what I'll do, since that's a hot mess, is just kind of scroll down, pause at any point here. If this is so much easier to read, which I expect it is, or if you wanted to add anything. Look at how neat my writing can be when it wants to be cooperative. Let's do this even. Okay, so I'll pause there if you want to write it down. A little further, there's the end of it. So hopefully you can see all of those points on that. Okay, so we're gonna zoomy zoom. What's our status here? I'm gonna kind of break this lesson into 2 parts just because my computer gets stressed out when it's too long. So I think we'll do up to my slide 6. So we'll do this number 2, then we'll do up to slide 6, and then we'll get on to the last couple in a separate video. So sketch a graph of the function. So maybe let's just add the word algebraically. Meaning you're obviously going to punch it in your calculator and kind of plot it out and know what it's going to look like. And that's not at all cheating. So please do that. Use your calculator, but do the whole process as well. So we're just going to go through the exact same steps. Now we have some a little bit of a different graph, so we'll see how it changes. So our y-intercept is our c value. So our y-intercept, let's see if I can get it right this time, is at 0, -2, not -2, 0. We know, so our a value right now, that's the value in front of that x squared, is a positive one, just like the last one. So a is greater than 0, not greater than or equal to 0, just greater than 0. So it's going to open up. The x-intercepts. We need to factor it in order to be able to determine the x-intercepts from here. So again, factoring by inspection, we're looking at two values that multiply to be equal to -2 and add to be equal to a +1. If they multiply to a negative, one needs to be positive and one needs to be negative. And since it adds to a positive number, we know it's going to be +2 and -1. So again, this is just factoring by inspection that we practiced. And then what we're going to do is we're going to analyze what makes each of these factors equal to 0. What makes x + 2 equal to 0, and what makes x - 1 equal to 0. You might already be detecting it real fast and being like, okay, that makes perfect sense. It's just the opposite sign, and for this point right now, that does work out. So if I subtracted 2 from both sides, x is equal to -2. If I added 1 to both sides, again, what you do to one side of the equation, you have to do to the other. X is equal to +1. So my x-intercepts are at -2, 0, and +1, 0. The axis of symmetry, there we go. The axis of symmetry, again, like we did with the last one, it's halfway between your two x-intercepts, or any 2 points that have the same y value. So -2 + 1 divided by 2. So that's our two x-intercepts. Adding them together divided by 2 is going to get us our halfway point. So our axis of symmetry, so -2 + 1 is -1. -1 divided by 2 is -1/2. So our axis of symmetry is along the line x equals -1/2. Sorry, I could be plotting these on as I go. I'll come back up and we'll do it after. So the maximum or minimum, again, if it's opening upwards, we're going to have a minimum, not a maximum. And so, again, the other word that we use, so we use minimum and maximum. We'll also use the word vertex. So in this case, our vertex is a minimum. The vertex will be on the axis of symmetry. So sub in that, x equals -1/2 to the original equation, which I don't remember. X squared plus x minus 2. So, So -1/2 squared plus -1/2 minus 2. Oh, let's see where my math is at with no calculator. So -1/2 squared will be +1/4 plus -1/2 is -1/2 minus 2. Okay, so this is me trying to do mental math. So if I have a quarter and I take away a half, now I'm at -1/4. And if I take away another 2, y equals negative 2.25. This is me cheating. Ah, yay, I did it. So, nope, not that one, this one. So y equals negative 2.25. So our minimum value is at x equals negative 1/2, y equals negative 2.25, 2 1/4. And our domain and range. So it's probably easiest to graph that, and then it's really easy to view. We know our domain for something like this. It's going to be x is an element of the real number system. Our range, actually you don't even need to graph it. So since we have a minimum value, we know what we're going to need to say that x needs to be greater than or equal to the y value of the vertex. So trying to graph these on, I'm just going to scroll over to this because it's like a million times easier. This is, okay, here we go. Let's slow it down. So once we graph all those things out, so again, does it not let me write on this? Nope. All right, Adobe doesn't let me write on my tablet, so that's not so good, but can you see me swirling, I wonder? Oh, all right. So we have each of those points that we filled in there. So we have our x-intercepts based on our factoring. We have our y-intercept based on that c value. We have our axis of symmetry being negative 1/2 or negative 0.5. We have our minimum and maximum. Not minimum and maximum, it's just a minimum, is at negative 0.5 and negative 2.25. So when you kind of sketch it out, nope, it would look something like that. All right, so I'm going to take a little break here. I think that's the next part. Oh no, I wanted to do one more slide. We said one more slide. Oop. So why will finding the x-intercepts of this beast be more challenging? And so when we would try to do this, when we would try to factor it, 8x squared minus 10x minus 1. So in this case, because a is not equal to 0, we need to factor by decomposition. You can look back at your review stuff. Remember what decomposition means is we're going to be splitting the b term into two parts. So when we're doing decomposition, we're looking for something that multiplies to be equal to the product of a times c and adds to be equal to b. So we're looking for two numbers that multiply to a times c, so that's 8 times negative 1. So multiplies to be equal to negative 8 and adds to be equal to negative 10. And so you could sit here all day and not be able to come up with something that satisfies this. So it is not easily factored. That doesn't mean necessarily that there are no solutions to it or no x-intercepts. It just means that they're decimal places. They're not nice, even, round numbers, so they're not easily factored. And we'll see how that can become a little bit easier, ways that we can kind of solve that. So not easily factored. There's no two numbers that multiply to be equal to negative 8 and add to be equal to negative 10 that are nice whole numbers that we can think about. So now I will take the break that I was talking about. I'll scroll through this key. No, I guess it doesn't really matter. But oh, that was the key for that one. So this quadratic is not easily factored. So by decomposition, there aren't two integers that multiply to be equal to negative 8 and add to be equal to negative 10. So I'll come back with some of the other ways that we can algebraically work through solving or sketching a graph.